Hello everyone, welcome back to Structure Expert. Today we continue to tall building lecture. Now let's start. From previous tutorial we discussed about the modified stiffness, and now let's continue to more detail about the modified stiffness. In the modified stiffness, specific for the earthquake but not specific for the wind load. So we use this value also for the wind load, apply for the wind load. For the modified stiffness, IG is the cross, okay, the cross is the uncracked. So when we use the modified stiffness, we distribute it 0.9 multiplied with IG, we distribute it 10%. And for the pressure measurement 0.8 Ig, so we distribute the stiffness 20%. Now let's continue. The effective stiffness of reinforced concrete for the member beam, non-pre-stress, beam pre-stress, column in compression and column in tension, wall and diaphragms, and crack. The flexural stiffness, it depends on also on the percentage of compression in member. When the concrete column is in compression, the modified stiffness we use 0.7 CD is the design modulus according to the Europe code. You can check. For the beam non-pre-stress, we use 0.5 CD IG for the energy or the uncracked section. And for beam pre-stress, we use CD multiplied with IG. For the column in compression, we use only 0.7 CD IG. Column in tension, we use 0.5 CD IG energy cross section, we use uncracked cross section for the energy. Wall and diagram uncracked, so you have to verify the sigma T to make sure it less than SCTM. And wall and diagram crack, you have to modify it to 0.5 CD IG. Sigma T, you verify it in tensile stress. If tensile stress in film software greater than SCTM, so this wall is correct. For the AC, is the cross section area of the concrete, and AW web cross section area, and LCD design value of the concrete compressive modulus. SCTM mean value. Yes, SCTM is the mean value, and for the LCD in a zero code, we use LCD is equal to LCTM divide 1.2. Okay, now let me say it. For the LCD, this one for the ultimate limit state, but for the circuit you can do it the same. LCD is equal CTM divide 1.2. Yes, you can check more detail in my tutorial about cantilever column design. Yes, this one in my tutorial 3 you can check about how to analyze P data effect in etab, and LCM, and LCD is equal LCM divide 1.2. We use the LCD is equal LCM divide 1.2 for the ultimate. Now LCM, let's correct it. LCM, yes. And for effective flexural stiffness recommendation by Poley and Brisley 1992, it also depends on the members. Beam rectangular flexural stiffness, you can use 0.4 LCD multiplied with IG, and for the T or L beam 0.35 LCD multiplied with IG, and column in compression. In a case high compression, NRD ultimate load applied on the column greater than 0.5 SCD multiplied with AC. So we use 0.8 LCD. In the effective stiffness of reinforced concrete recommended by the IS Strat, ASPS, and ASCE, the column in compression use 0.7 LCD multiplied with IG. But for the Poley and Brisley, they divide column in three, yes, column high compression, average, and column in tension. For column in high compression, you can use higher stiffness is 0.8, and column in average compression you use 0.6 LCD multiplied with IG, and column in tension, so you only 0.4. In the above slide we use 0.5 for the column in tension. For the recommendation we use 0.4 LCD IG. And for the cantilever wall, so you have to use the formula to check for the flexural stiffness modified 100 over SYD. SYD is SY of the shear strength of steel divided by the safety factor, and ED or the ultimate load applied on the column divide SCD multiplied with AC and multiply with the LCD IG. For the coupling beam conventional reinforced, we use the formula to estimate the flexural stiffness. Coupling beam diagonal reinforcement, when you add diagonal reinforcement, so it increases 2 times 0.4. use the formula. For the AC cross-sectional or the reinforced concrete, LCD design value of the concrete compressive modulus, and SYD design value of the shear strength or reinforcement in MPa. This table gives recommended value for concrete member given in Poley and Brisley 1992. Now let's check the stiffness or effective stiffness. It depends on the percentage of rebar in the member. Now you can check for the axial load. When you apply the axial load, this one the axial ratio, axial load in column divide on AC SCD, and the stiffness ratio 0, 0.2, 0.4, 0.6, 0.8, and 1 if 100%. And the actual load ratio is 0, 0.1, 0.2, 0.5, and 0.4. You see here, when you use a higher percentage of rebar in a section, in column or in wall, so the percentage of stiffness also increase. and when you use the 0.2, okay, the 0.2. Now this one is a percentage of the rebar, 1%, 2%, 3%, 4%. In the case you use 0.5%, you see here the the stiffness ratio is lower than when you use 4% of rebar in the same member. So the rebar in the member also increase the stiffness of the member. In a tape or in other software, you always use modified stiffness for the concrete section only, not include for the rebar. To make sure, you have to verify it by yourself when you include rebar in section and run analysis again to check deflection and it reduce deflection or not. So you have to verify it. The stiffness, actual ratio, percentage of the reinforcement. This is the model in etabs. Now we have to verify about the tensile strength, in a member. We refer to flexural member in the wall or core wall. Now we have to check about the core axis. You have to show about the core axis in the flexural member. We have to check about the stress. Now let's zoom in to check the red axis, the red local axis is local axis 1, and the green axis, the local axis upward is the local axis 2, and this local axis is local axis 3. I use automatic option in etabs. Now you see here, when you play it automatically, you have to check about the local axis of element to make sure it the same direction. Easy to check it. Indicate the local axis is not the same. Now let's check. We check one side. Local axis is outside, and in this panel, the local axis is inside. You can check here, and the direction of it in this direction, in this panel in this direction. And for other side, you can check this one, the local axis is inside, local axis and local axis is outside. So when you use a different local axis direction, you have to check in different compression and tension to avoid error when you verify the compression and tension. It is a very common area in structural for structural engineer to analyze stress result. To avoid the error, you should assign the local axis in the same direction. Okay, it's the same direction with the global axis. It's easier to verify. Now we will open in a tab to check it again. Continue to the next slide. We don't know the stress in the software is compression or tension sign is minus or plus sign. So you can test on a column, on one panel column, to verify when you apply the compression load, and the local axis is upward. So the result is in positive or negative. Now let's check. So the result of compression in a tab is value is negative. I apply for the S11. You have to check S11, the red local axis S11. This stress is axial stress. Direction is perpendicular to S2 direction of local axis 1. And the compression stress is minus 138. Now let's check for other load. We apply the same load but different direction. We use the 10 upward force 5000 kilonewton in one node. Now let's check. This is the direction of local axis in the wall, and the result of the tensile stress is positive value. At the bottom is 136 megapascal, and at the top is 128 megapascal. So the tensile stress in the tab is positive, and compression stress in the tab is negative. Now you can check in the flexural member for the core wall. Let's continue. This system, in this building I use the modified stiffness column is equal 0.5 E multiplied with Ig, and wall is equal to 0.35 multiplied with Ig, and beam slab is equal to 0.5 E multiplied with Ig. You can check in my tutorial. I model it completely from the beginner level to complete level by using a tab. You can check. I use the modified stiffness for the member. You can verify it. Let's check in my tutorial. And why we want to check about the local axis? It's easy to check about the stress. So when the local axis direction in default tab, I use automatic option to place the core wall in the tab. The local axis in the wall is local axis 2 is upward, and local axis 1 is the direction. But when you draw it manually, the local axis 1 is upward and local axis 2 in this direction. It's no matter the local axis in any direction, but you have to show the local axis on the element you want to check. It's one the local axis 2 in upward, so I had to check about local axis 2. Yes, we check on the surface. We check the correct stress or tensile stress in the circuit limit state. Don't check it in ultimate limit state in the correct, because we concerned about stress. You have to check it in circuit. If you check in circuit tensile stress is not appear the tensile stress. This wall or flexural member is not uncracked. So this member is I'm sorry. When you verify the tensile stress in the flexural member and the tensile stress is not appear, so this member or this flexural member is uncracked. Okay, is uncracked. Now let's check. We check S22. S22. The result of S22 is, you see the red color is around 5.5. Yes, 5.5 in compression. So the core wall is compression. No tensile stress appear at the bottom. We have to check about the critical wall from the basement to the second 4-5 floor. In this floor we can can appear crack section, can appear the tensile stress. So you have to verify it. Now we have to verify it's all. Let's check together. The first case we check about the S22 and the result. This core wall is uncracked section. Uncracked section. So you can use the IE for the stiffness, and You can also verify for the S11, but we focus about the S22 for the tensile stress. Now let's check. You have to make sure the tensile stress is less than the design tensile stress of the concrete. SCTM is the design tensile stress of the concrete. So it indicates the wall is uncracked. You can design uncracked use LCD multiply with IG. Now let's continue. Yes. When you check the service load in with the wind y direction, the about slide we check the service load in with wind x direction. So now let's check with the wind y direction S22, and at the bottom the stress is around 5.6. The compressive stress. No tensile stress appear in this wall, so we can consider this wall is uncracked section. And after you verify the section is cracked and uncracked, you can continue to check about the natural frequency. This natural frequency corresponding to the modified stiffness. Modified stiffness of column is equal to 0.7 E multiplied with IG, and wall is equal to 0.35 E multiplied with IG, and beam slab is equal to 0.5 E multiplied with IG. Because the wall is uncracked, so you can use this stiffness again. Let's change E, use the wall. Now you can change the wall. Let's check in the about slide. The wall ECD multiplied with IG, or you can use the option for the wall 0.9 IG. Wall, now let's say I want to use 0.9, or you can use 1 IG, 1 E IG for the wall. And for the beam slab also the same. You can check it for the column. Yes. Now let's check it. For the column in compression, okay, now you can keep it. You can change only for the wall. For uncracked, you can keep CD multiplied with IG. After we verify the tensile stress, it less than allowable design tensile stress of the concrete. But actually in our model, no tensile stress appear. You can check in model. And for the beam, you can keep it. For the beam, okay, beam you can keep it 0.7, and column you can use 0.9. okay, in the case column you can use it 0.9, and beam slab you can keep it 0.7. Okay, now after we verify with the tensile strength in a structural member, you can change this material, change the section stiffness again and check the frequency. This frequency is the result corresponding to the modified stiffness we used in the previous tutorial. Column is equal to 0.7 I, and wall is 0.75 I, and beam slab is equal to 0.5 I. Now after we check the tensile stress, you can change the thickness to column is equal to 0.9 and wall is equal to 0.9 over 1 I, and beam slab you can increase it to 0.7 I. After that, you run it again and recheck about the flexural stiffness or the overall stress. Okay, overall stress and in interstory tree you have to check it again, and after that you have to verify about the natural frequency. The natural frequency is very low, kind of acceptable. We have to increase the stiffness in the member, but before you increase the stiffness of the member, you have to change the stiffness to modify the stiffness. Use the stiffness for the column, for the wall, and for the beam, and run analysis again and check for the frequency and what is different when you change the stiffness. The frequency is increased, so how much it increased, and verify it again is acceptable or not. For the model 1, the period is 2.54 seconds and frequency is 0.79 cycle per second. And for the node model 2 is 2.37 and the frequency cycle per second is 0.42. For those two mode shape, the frequency is lower than design recommendation. You can increase it. For the model shape 3, the frequency is 1.064. This one is a very good result. We want to use this result around 1 Hz, or you can verify it is lower than 1 Hz is acceptable or not. You have to check it again, but you can verify it for the cantilever. Okay, cantilever structure. Check in my previous slide. Yes, structural frequency in the first cantilever bending mode. Okay, in the first mode of the structure sitting a frequency lower than 46 over h at the total height of the building. Yes, you can check here. The result is very low. Calculator 46. Check. Let me. The total height of the building is 3 multiplied with 32 is equal to 96. Okay, now let's check it. Because we have 2 basements, you can use only 3 multiplied with 30 floor. It's okay. 46 divide 90, and the result is 0.5 hertz. 0.5 hertz. And our result is 0.39 hertz. So you have to increase it stiffness more. You have three options. The first one is to decrease acceleration, and second, you can check about my slide by dynamics. Okay, you can decrease the rate of loading. You can add the stiffness on the member or on the structure, or you can increase mass. So the option is difficult. You have to increase mass on a specific floor, on the top floor, and the stiffness, you can increase the stiffness by increase the section of flexural member, or add more wall or shear wall, and the rate of loading. This one naturally for the building we can reduce it. You can add damper to reduce the magnitude of the seismic overload, to reduce the amplitude of seismic overload. Now let's check about the mode shape. This is the first mode shape 1, and the natural frequency is 0.39 hertz. And the mode shape 2, the natural frequency is 0.42, and mode shape 3 is 1 hertz. This is the mode shape 3. You can check for the all mode shape. Now I check only for the 3 mode shape. Here's subject wall for the mode shape 3. Now let's check for the model. Okay, click on set display option. You can turn the column, beam, and floor, or null frame, horizontal textural dimension, apply. Okay, apply. Diaphragm extension, apply. Okay, now we want to show only for the wall. Now let's check it. Click on display option again, object assignments, show local axis on the cell element. Now you can check here the local axis. In this panel, the local axis of Z is inside, and this panel, the local axis Z is outside. Direction is outside. And for this panel, the direction of local axis Z is inside. So when you design all the local axis, it's difficult to check. You can modify the local axis. This one you can do the same. The local axis Z is inside, but we do not focus about this. You can change it manually by select the cell element and assign the rotation of local axis. For me, I can check it easily. I know what is the sign convention for the software. You can check it, the sign convention, the local axis Z, H, and Y, and how to verify it. Now for this panel, the local axis Z, or in a tab called local axis 3, is outside, and for the panel is inside, and for the panel is inside. So for the opposite core wall, the also opposite local axis, you can check here. Now let's check for the local axis 1 and local axis 2. So we have to check about tensile stress inequality 2. Let's click for the display stress and click on combo. Combo we do not check in the ultimate, we check in the service. Click on the service and bin it. And result for we do not check result for, we check the stresses. And let's check the S22. Okay, S22 apply. Now you can grow over the cell panel. The result is minus 4.24, 4.74 is around 5 in compression. DBU is in compression. For other side also in compression. Okay, now let's check this side. Compression. So DBU is acceptable. Yes, no tensile stress appear for the service with the wind its direction. Now let's check for the service with wind y direction. Okay, now let's check it. The compressive stress. Okay, compressive stress. Okay, compressive stress. So no tensile stress involved. This wall is uncracked section. So you can modify the stiffness of the member to uncracked section and run it again to verify the overall trace and inter-story trace. Also verify the natural frequency again. Now let's check for the compressive stress. Y compressive stress. The maximum is around 5.60. Let's quick calculate it. The concrete strength we use 45 multiply with the national niche. We use national niche of UK 0.85 for the concrete and divide for the safety factor of concrete gamma C 1.5 is equal to 25.5. So the value of the compressive stress is 5.6 is acceptable. Okay. Thank you for your watching. Thank you.